going to go ahead and talk about 1.2 transformations of linear and absolute value functions. Now, we've already talked about linear functions when we were talking about transforming functions. So I'm going to go ahead and skip that and really focus in on the absolute value transformations. So just a quick review. Remember function notation, y and f of x, those can be used interchangeably. So when we write something in function notation, it's f of x, supposed to be a parenthesis, equals the absolute value of x. Okay? And then when we talk about output and input, output, remember, is our f of x or our y, and our input is x. So say we're building a t-chart, we have x, we have f of x, we can plug some values in. We can say, well, if our input is 0, substitute 0 in for x. The absolute value of 0 is 0, so our input of 0 gives us an output of 0. If we were to say plug in 1, an input of 1 is going to give us an output of 1. It's kind of boring that way with these. And I guess if we want to really make it a little more exciting, we could plug in, we can input -1, and the absolute value, remember absolute value means distance from 0. The distance -1 is from 0 is 1. An output of -1 gives us 1. If we kept doing that, we'd find that -2 would give us 2, and 2 would give us 2. And so when we were to graph that, you'd end up with these points that look like this. Very familiar, that is the linear part of the linear function, f of x equals x. And like this, which also hopefully is familiar, that is the linear function f of x equals -x. Okay, it'd be nice if I hit the points there, but I think we get the point. Okay, no pun intended. So there's f of x, and I'm just going to label it as f like that. And so now if we talk about transformations, we're going to go ahead and add to the input. So I'm going to go ahead and put that graph back up there. Let's go ahead and put those parent functions back, that parent function back in. We're going to add to the input. And really adding to the input just means that I'm going to take, and I am going, or excuse me, add to the output here. Okay, and adding to the output means that I am going to take, and I am going to add something to every output value that I originally had for my parent function. So just a real quick sketch of that parent function so we have something we can focus on. Okay, so if I'm adding to the output, I'm actually adding to f of x. So if I were to call that in function notation, I'd say g of x is equal to f of x, and I'm going to add something to it. We'll say we're adding 2 this time. We're going to add 2 to the output. All right? And really, if we look at that in table format, we could say, well, there's x, there's f of x. And in terms of our original table, we had 0, 0, 0. We had 1, 1, 2, 2, -1, 1, and -2, 2. And so since we're going to add to the output, we're going to go ahead and, let me switch colors up on that. We're going to go ahead and add that 2 to each of our output values. And so in graphical format, it looks like more like this. So here would be g of x. So 2 plus 2 is 4. 1 plus 2 is 3. 2, 3, and 4. So in graphical format, we take this -2, 4, and we plot it. We take the -1, 3, we plot it, and you can see in a picture format when we start plotting all those, and I'll continue out the pattern. In a picture format, you see that that graph is actually looks like, if you just focus on the points, it looks like each of them moved up 2 points. So it actually did a vertical translation, and that's actually what happened. Okay, so when you add to the output, it actually moves our graph vertically. This was a vertical translation up 2. Okay, and so remember, output means it happens on the outside of the parentheses when we're in terms of our function notation. So if you think of here's the inside of the parentheses, well, this happened outside of those parentheses. And whatever happens on the outside affects your y-axis. Okay, and it moves it vertically. All right. That's a pretty easy one to see. When we start talking about adding to the input, so if we take our original function, our parent function again, and I'm going to try to trace it without putting a bunch of points in it. Actually, like I got that leg a little better than when I actually put points on. There's F, there's F. We'll plot some points. Okay, so graphically we have that. Now when you're adding to the, when we're actually adding to the input, remember input means inside, or it's the same as thinking of inside when you're dealing with function notation. So we're going to say f of x, and let's say we add 2 this time again. It's happening on the inside of the parentheses. So inside, so when we write it in function notation, rather than being outside, like we had on the previous one, where it happened on the outside, kind of got cluttered there, so this was your outside. Okay, where it happened on the outside, when we're dealing with adding to the input, it's happening on the inside. And so if we were to look at that in terms of writing it out, we'd say, well, this x plus 2, that's an input value, so it's inputting for x. So we're going to take, and whatever we had, wherever we had x in here, we're going to plug in that x plus 2. Substitute that in. So to write it in kind of a nicer, neater format, it would look like that. Okay, and so it's a little harder to see this one in a table, but if I was to build a table for it, I can say, well, I have g of x, or excuse me, our inputs of x, where I had 0. Let's focus on those same inputs. Okay, where I had 0 before, I put 0 in. 0 plus 2 is 2. Well, and the absolute value of 2 is 2. Okay, so an input of 2, or excuse me, of 0, not of 2. An input of 0 gives me an output of 2. An input of, let's go ahead and try a different input here. So we'll put 1 in this time. 1 plus 2 is 3. Absolute value of 3 is 3. Okay, an input of 1 gives us an output of 3. Okay, and an input of 2 gives us an output of 4. Now, some would look and go, well, this one's changing again by 2. Well, let's see if we let's go ahead and put an input, and I know that I'm getting kind of messy with my inputs here, but an input of -1. -1 plus 2 is 1. Gives me an output of 1. Well, before, -1 gave me an output of 1. So that's kind of weird. Well, let's go ahead and try -2. -2 plus 2, input of -2 gives me an output of 0. Okay, well, that's kind of weird too. So let's go ahead and graph these, see what it looks like. So if I were to graph -2, 0, I'm right there. If I were to graph -1, 1, I'm going to graph 0, 2, 1, 3, and 2, 4. The problem is, right now, all I see is one branch. And I could keep going, but I'd end up getting something that looks like that. So let's try some of these values on this side. So let's say I put -3 in. Input of -3. -3 plus 2 gives me an output of -1. Absolute value of -1 is 1. Aha, my graph is now turned. And if I put -4 in, I get an output of 2, and so on. And so what you see here is this this line, which I obviously did a horrible job at drawing there. Let's fix that up. This line right there for G is a little better. And you see that my graph is actually, this point moved to there, this point moved to there. My graph is actually moved horizontally. You even see that on this side over here. It's been a horizontal translation left 2. Now, in the past, we've talked about like the +2 kind of makes you think that maybe you should go towards the positive end of the x-axis. This is the negative end. However, everything's kind of backwards on the inside of your parentheses, so you actually move towards the negative side. And really, you got to think about whatever will make this 0 in here. So like -2 + 2. So that's kind of a whole nother conversation, but my vertex would move to -2 there. Okay, so it's a horizontal translation. Anything that happens inside changes your graph horizontally and changes the input. And if it's adding on the inside, then it's a translation. And just like if it's adding on the outside, it was a translation. It's just on the outside, it moves it vertically. And it changes it on the Y. Okay, so that kind of gives away the multiplying by the output. And by the way, this is messy work. I'm going to show you a neater way to show some work here. Let's say we're multiplying the output this time. And once again, it's a lot easier when we're dealing with an output value, because we can really take our function, we can graph the parent function, okay, and let's go ahead and put those points that we've been dealing with back in there. That's not an amazing graph of it there, actually. Really fairly poor graph of it, at least on part of it there. So, okay, but that'll do for what we're doing here. Okay, so when we're dealing with multiplying the output, remember it's output, which means it's happening on the outside. It means we're going to take, and in function notation, we're going to multiply on the outside. And so let's just stick with our 2. Okay, so we're going to multiply by 2 now. Output is going to affect it vertically, so we automatically know this is a vertical. Okay, it's going to change our graph vertically. And look, if we were to plug in what f of x is, f of x happens to be absolute value of x, so it just means we have 2 times absolute value of x. That's equal to g of x. And so if I'm going to graph this, I have x, I have 0, I have 1, I have 2, I have -1, and I have -2. And so I'm going to plug in 0 for x. Okay, and our 1, our 2, and our 2. Those were original outputs for f of x. Remember, we're now going to multiply that by 2. So that means I'm going to go ahead and multiply all of our parent function values by 2. And so that's going to give me new outputs, which we were calling g of x. So 2 times 2 is 4, 2 times 1 is 2, 2 times 0 is 0, 2, and 4. And so graphing those, notice this is a lot neater of work. Graphing those, I have my, whoops, let's get out of this. Fix that real quick. Okay, we're going to go ahead and go 0, 0, -1, 2, and I want to go back to my correct color, -1, 2, 1, 2, and 2, 4, and -2, 4. Notice we end up with a graph that does something like that. Let's fix that up here. that one's G, that one's G. And really, you have your graph is actually done what's called a vertical, and it's a vertical stretch by a factor of 2. And I'll show you how that looks if I can get a straight line drawn in here. Okay, and so this point that was 1 unit away is now 2 units away. And this point that was 2 units away is now 4 units away. This point that was 1 unit away is now 2 units away. And this point that was 2 units away right here is now 4 units away up here. So really it's been a vertical stretch, BAFO, which we say BAF by a factor of, try to abbreviate it, we've talked about that a bunch, by a factor of, so BAFO 2. It means it's stretching everything away from the x-axis. It's stretching everything away from this axis. It's making every point twice the distance. So for instance, just to make sure we're clear on that, a point that was, say, originally 3 units away would now be 6 units away. So it's stretching it, it's pulling it out away from the x-axis up there. Okay, so it's happening vertically again because it's on the outside. All right, so let's move on to multiplying by the input. Multiplying by the input, I'm going to summarize here, happens on the inside, which means I'm going to take f of x, it's going to be equal to the absolute value of x, okay? And so when I look at that in function notation, it's now going to be g of x is equal to f of x. But if I'm going to multiply it, if I'm going to multiply the input, that really means I'm going to, rather than having the x in there, I'm going to go ahead and multiply that by something. And we'll go with 2 again. Okay, and so this 2x is going to replace x here. So really we'll have absolute value of what was x is now 2x. That's going to be my g of x. And if I were to build my table again, x, g of x, and actually let me give you a little workspace this time for dealing with this. Okay, which means really I should erase all that, go a little more room here, kind of build a table. So this is going to be x. We'll have g of x, and our rule is absolute value of 2x. So we'll put that there, and then we'll say g of x. And so that gives us some space to keep our work organized. So if we have, say, like 0, 2 times 0, absolute value of that is, well, that's 0. And if we put 1 in, well, that's absolute value of 2 times 1, or 2, which is 2. We put 2 in. That's the absolute value of 2 times 2, which is absolute value of 4, which is 4. Okay? And if we have negative 1, we have 2 times absolute value of negative 1, which is, well, that's negative 2. That's also 2. And negative 2. 2 times absolute value of negative 2 is negative 4, which is absolute value of negative 4 is 4. And so if I plot those points, there's my 0, 0, my 1, 2. Oops, I switched colors there. So my 1, 2, my 2, 4. Okay, and some people would look at that and go, hold on, that looks really, really similar to that one. It's true. It's just we now know that if it happens on the inside, it's happening horizontally. This is a horizontal. And everything's backwards on the inside. So if you recall, when we multiply by 2, we're actually doing what's called a shrink. A horizontal shrink by a factor of the reciprocal of that, 1/2. So it's taking, let me show you picture-wise what's happening. So if I put my original function back up here, I think I'll just put the dots. Okay, that should be enough dots there, enough points. Okay, so if I have my original function there, really, let's go ahead and switch colors here. So this point that was 2 units away is moving inward to now be 1 unit away. This point right here, what was 4 units away, is now moved inward to be 2 units away. And when I say away, let's focus on that one. That one's 6. It would now be 3 away. And the same thing's happening over here. When I say away, I mean away from the y-axis. So let's give me a different color highlighter here. Everything is doing a horizontal shrink by a factor of 1/2. It's moving, it's being squeezed towards the y-axis. All these points are squeezing in towards the y-axis. They're compressing towards y. Okay, so it's a horizontal shrink by a factor of 1/2. Okay, and we just know that it's happening horizontally now because it's multiplying by the input. Now, reality is with this one, this graph, and the previous graph, the vertical stretch by a factor of 2, pictorially they look the same. And in fact, even when you look at your tables, they look the same. It's just in your equations there, that one and that one look different, but they're affecting in the exact same way. That won't happen with every function that you deal with when you're dealing with a vertical stretch and then a horizontal shrink, but it just so happens that it does with absolute value functions. Okay, the last one is just reflecting the output and reflecting the input. Okay, and so let's deal with those. I'm going to kind of go through those fairly fast. They're usually generally the easier ones. But if I'm reflecting the output, so I have my original function. Okay. And once again, I had a hard time drawing the line. For some reason, I keep going off base just a little there. Okay, so there's F. Now, if I'm going to reflect the output, remember its output means it's going to happen on the outside. So if I have my g of x equals f of x, it's going to happen out here. So what I had before, it's very easy to see it table-wise. Remember, if I have my original parent function points of 0, 1, 2, -1, -2, the ones we had since the very beginning, that we did first. Now, if I'm going to change it and reflect the output, that means all those points, all those outputs are going to become negative, which means my g of x is now going to be -2, -1, no such thing as -0, so it's just going to be 0, -1, and -2. So really it takes this graph and it reflects it down here. Okay, and so you get a graph that's doing a horizontal, excuse me, not horizontal. Sorry, it's happening on the outside. A vertical reflection over the x-axis. So all these points, since it changed vertically, these points moved downward. They just flipped over the x-axis. So what was up here moved down. Okay. All right. So it's a vertical reflection over the x-axis. We know it happened to the output. So it happened on the outside, and that affects us vertically. Now, when I'm reflecting the input, it's again going to see a bit weird here. You're going to have f of input means it happens on the inside. Negative x like that. That replaces that x, so we end up with absolute value of negative x. Well, we know that if we're dealing with this, notice that if I were to create my table, not f of x there, but if I have my x and my g of x, I would end up with 0, 0. I put 1 in for x, I get 1 out. I put 2 in for x, I get 2 out. -1, 1, and -2 and 2. Well, what's kind of weird about that is here's my parent function. And then when I graph my transformation, 0, 0, 1, 1, 2, 2, -1, 1, -2, 2, it's the exact same thing. Well, and that's because this is a horizontal. We know it's horizontal because it's happening to x, and x runs horizontally. Horizontal reflection over the y-axis, which means what was here moved over there, and what was here moved over there. So these points, in essence, just swap places, which means your graph looks identical. Kind of weird, but that's what happens. Now, if the graph is translated first and then reflected, you would see the changes a lot easier. All right, thanks for bearing with it. That is transformations of absolute value functions.